Welcome back to Carneades.org. Today we're going to be continuing with our series, Blunting Occam's Razor. In this video we're going to be looking at what is the paradox of curve fitting. Now, the paradox of curve fitting is a paradox for identifying the best model to fit a particular set of data points. The paradox is simply that there's no way to determine, based only on the data, which model or which curve is the best fit without some assumptions. Some have attempted to use Occam's razor to address this paradox by arguing that certain curves, certain equations, etc. are simpler than others. In this video, we're going to cover that initial paradox, some attempts to solve it using Occam's razor, why those attempts fail, and then we're going to look at a more general version of Occam's razor, a weaker version of Occam's razor that has similar statistical techniques that are attempted to use to justify it, and why those statistical techniques fail to justify this kind of weaker version of Occam's razor. Let's take a look. So, many scientific experiments try to postulate an association between two measurable quantities. The more of X you have, the more of Y you will get. These data are often placed upon a scatter plot, and some line of best fit, some prediction line, is drawn on the graph to represent all of the unmeasured points in between. This can, of course, be done with many more dimensions than two. You can have a lot of things influencing a single output, but we're just going to stick for two for simplicity's sake. The overall conclusions apply to the additional dimensions as well. This line is both used to explain the relationship between these concepts and to predict future points. Sometimes that line is straight, sometimes it is curved. The paradox of curve fitting is that there is no way for us to determine what the right model is to describe that line. Curvier lines explain more points, but are more complicated, while straighter lines hit fewer points, but are simpler. To be clear, this is not a paradox claiming that if we assume the relationship is linear, we can't find the line of best fit, but rather a paradox for having an objective way to decide which model, linear, quadratic, exponential, etc., and which covariates to include are the best. Let's take a look. So, for example, there are several lines that we could draw through this graph to explain these points. We could draw a straight line, a curved line that captures most of the points, or a more complex line that hits them all. The paradox is there's no way to determine which of those three lines is the best. Now, in this, it's important to make a distinction between identifying the line of best fit given a certain model and being able to identify the best model to begin with. The paradox is for the second problem. Once you have an equation, there are different statistical techniques, such as ordinary least squares, you can use to find the coefficients for that equation. Deciding whether a quadratic or a quartic equation better explains a particular data set is underdetermined, and that's the problematic paradox. So, one tool that has been attempted as a solution to this problem is Occam's razor. Harold Jefferies attempted to do this by arguing that equations had different degrees of complexity, objectively, and that more complex equations had lower levels of prior probability. Check out our series on Bayesian epistemology for more on that. Basically, Jefferies was arguing that quadratics were less common and therefore less likely because they were more complex, because they had more variables that could be wrong. Based on Jefferies' theory, equations with higher coefficients, higher orders, and higher degrees were more complicated. In this model, linear equations were simpler than quadratics, quadratics were simpler than cubics, etc. This was built on the intuition that the more things there are to change, the less likely they are to all be right. However, Karl Popper raised a key objection to this claim. He argued that all linear equations are simply quadratics where the coefficient on the squared term is 0. Essentially, ax squared plus bx plus c is the same as bx plus c if a equals 0, and therefore all quadratics are just cubics with 0 for the coefficient on the cubed term, etc. If all linear equations are a type of quadratic, there's not an important way to distinguish between their likelihood. If we have a question about what is that a value going to be regardless, because all we're doing when we're saying that an equation is linear is we're saying we found the a value and it's 0, then there's not this same sense in which there's something importantly different about these two types of equations, but rather linear equations are simply a subset of quadratic equations. Linear equations have all the other terms, a squared term, a cubed term, etc., but all the coefficients just happen to be 0. This means that we do not actually reduce the number of things that we could change, since all the equations have those terms, and it's just as likely for those coefficients to be 0 as anything else. There's also another number of other problems with the idea that we can say, because we have two separate terms, there are more things really that are going on, because you can put things like the rational numbers into direct correspondence with the natural numbers, and which makes them denumerable, and so it's the same size infinity you're working with. And so if you just have a set of two natural numbers, you can actually put that into correspondence with the set of all single natural numbers, and so it's the same size infinity you're working with. And so there's not, even if we were to accept that the linear and the quadratic equations were somehow importantly different, the fact that you have those two terms isn't actually more complicated. You don't actually have more things to deal with. This gets into a lot of more complicated things that aren't necessary for eliciting the problem that Popper raised here. But if you're curious, check out our video on Cantor's paradox for more on that. Now, this does, however, build into another justification for Occam's razor, the idea that the more assumptions you make, the more likely you are to be wrong. If I make 5 assumptions that are all pretty likely, maybe they have an independent 90% chance of being correct each, I still have an over 40% chance that at least one of them is wrong, because 0.9 times 0.9 times 0.9 times 0.9 times 0.9 equals 0.59 chance of it being correct. As long as those are independent, it's allowed for me to multiply them separately to get the overall chance. And so there's a good chance that at least one of them is wrong, even though all of them were pretty likely to begin with. The more assumptions that I make, the greater chance it is that they are all wrong. Every time you make one additional assumption, assuming it's not perfectly certain, you will reduce your overall likelihood. Even if this fails as a justification for simplicity, for the simplicity hierarchy of equations, it might serve as a justification for Occam's razor as a whole. Now, there are a number of issues with this argument. First, it assumes that all of your assumptions have equal prior probability, which they rarely do. Rarely are you taking the same set of 3 assumptions and then adding to those assumptions a single other assumption that is slightly less than 1 likely. Assuming 3 plausible propositions is more likely to be true than assuming one very outlandish one. This gets back to the problem of conjoining premises to make fewer assumptions, though doing so will decrease the likelihood of that single assumption that you make. Conjoining very likely premises to make a single less likely one doesn't actually make it more likely. It's simply a bit of bait and switch going on. It merely makes it appear that the theory better satisfies Occam's razor when you're really just conjoining or connecting or looping in a bunch of things into a single premise that becomes increasingly less likely the more things you loop in there. And even determining this prior probability, what that initial probability is, that 0.9 that we had from the earlier example, is notoriously difficult to do, because you have to do it without making any assumptions or actually having any information, because that's your basic assumption to start with. And so prior probabilities, while extremely impactful on the way that you make choices and decisions, implicitly have no ability to be justified. We have a sizable video on the problem of the priors in our Bayesian epistemology series if you're interested in why this idea of prior probabilities is so problematic. Another challenging issue is proving the statistical independence of the assumptions, which is an assumption in itself and has some amount of prior probability that we probably can't determine, just like all the others. Generally, the assumptions you are making to support a theory are in some way linked, such that if one is true, the others may be more likely to be true. Usually, the assumptions that you have aren't fully independent, that they're relying on each other in some way, at least in real scientific theories. If they are linked in this way, making more assumptions may not lead to a substantially less likely theory overall. In general, this justification for Occam's razor is built on a Bayesian framework, which is very innovative, but has a lot of problems. As I've said a couple times already, check out our series on Bayesian epistemology for more of the virtues and vices of that framework. There's another principle that has been called Occam's razor at times that is arguably much weaker than kind of the Occam's razor we've been looking at so far. And it relies on this kind of statistical justification. Now, this is the claim that a single cause of a phenomenon is more likely than multiple causes. Note that this is importantly distinct from version of Occam's razor we've looked at so far, Because it's not about the elegance of a theory, how simply it's stated, nor is it about the parsimony, how many specific entities it posits. Rather, it's a very specific and in many ways weaker version of Occam's razor that's saying if you have a single phenomenon, it's better explained by a single cause than multiple causes. Let's look at some examples to kind of elicit why this is a persuasive version of Occam's razor despite being weaker. For example, if you smell smoke in your house, you feel heat in your house, and you hear a fire alarm going off in your house, all at the same time, you could conclude that these are separate, unrelated events, or you could conclude that they have a single common cause, i.e., your house is on fire. Occam's razor says that the simpler explanation, that your house is on fire, is the more likely. One might make a similar claim in science. It's more likely, according to this version of Occam's razor, that a patient's sudden illness is due to a single sickness rather than due to contracting two different illnesses at the same time. Now, a key part of this version is that the things are happening at the same time and in the same place. If you heard your fire alarm going off one day, saw smoke a week later, and felt your house getting warm the following month, it seems like you'd be very justified in concluding that these were different issues. If two patients on opposite sides of the globe who never met had different symptoms at the same time, you'd be unlikely to be justified in thinking that these illnesses were the same. This version seems to be less about Occam's razor and simplicity and more about proximity. And so it doesn't even really seem to be a version of Occam's razor at all, but rather a generalizing rule about proximity. One might generalize such a principle as follows. The closer phenomena are in temporal and physical proximity, the fewer possible explanations there are for them, and therefore the more likely those phenomena are to be explained by fewer causes. It's not really about simplicity, but rather about the simple limits of physical and temporal proximity. Now, this might be justified, not in reference to the simplicity of a theory, but in reference to the limitations of space and time. There can only be so many things in a particular place. And so if an event happens, if two events happen at exactly the same place at exactly the same time, there's only so many things that can cause them. The smaller that place is, the fewer things there can be. If there are two phenomena in a very small space at the same time, it's likely that something in that space caused them, and the smaller the space is, the closer those phenomena are temporally, the fewer possible causes there are, simply because there can only be so many things in a certain space at a particular time. Now, but even this principle, which is only weakly recognizable as some version of Occam's razor, relies on a certain degree of assumptions. First, it assumes that there is no action at a distance, both physically and temporally, something which quantum physics at least is called into question. Second, as with other versions of Occam's razor, it's difficult to define what a single cause could be. The cause of my smelling smoke, feeling heat, and hearing the alarm could be that there is a fire in my kitchen causing the smoke, there's a fire in my living room causing the heat, and a fire in my bedroom causing the alarm. Those could have been caused by separate actions of me leaving the gas on, closing the window, and someone striking a match. At what point is a fire a single thing as opposed to many different chemical reactions? What makes it a single cause when it is happening in multiple places at different times, burning different things, being made up of different materials in those different places, and had multiple causes itself? Third, while this might provide explanations for particular events, it's much weaker at helping to provide conclusions about general theories, which are often trying to explain events happening at very disparate times and places. All this is getting us is for a very specific subset of things where things are already proximate, whereas a lot of what science is doing is it's trying to take things that we can study in a lab and generalize them to different times and different places to try to understand the world. Fourth, even if very close proximity limits the number of options, it rarely ever limits them to only one. Even if there is a hard physical constraint on the number of things that could have caused a particular event, because there were only so many things in a certain area, rarely is the number of particles or atoms in an area only one, unless the area is very small. There's nothing that seems to point to one thing being more likely than two things to cause something, even if we're confident that there could not have been 100 different causes, because there are not 100 different things there. If there are two things in a location at a time when two things happen, it seems no important reason that there could that it's more likely that one of those things caused that thing to happen than the two of those things caused that thing to happen. In fact, it might be the conjunction of both of those things being there that was causing it, given that they were the two things there. And so while we might be able to say there simply aren't 100 things in this location at this time, and therefore it can't be 100 causes, it's hard for us to say it's more likely that it's one as opposed to two. Fifth, this begs the question against non-physically or non-temporally proximate explanations of phenomena, which might be able to act on things that are physically or temporally distant. We don't know if time travel of some kind is not possible. We don't know if there are not other kinds of matter that don't follow the same laws as we expect them to regarding what is in the same space. We don't know that substance dualism, for example, is false, and there aren't mental substances out there that can act on physical substances and therefore be in the same space because they are a mental substance that perhaps we're not observing. We don't know if physical substance is merely an illusion and mental substance is all there is, and therefore there can be lots of mental substance in the same place causing something. And so there aren't the same limitations that we face with physical space. And so we're begging the question against some of these non-physicalist explanations of the world. Whew. What do you think? Is there an objective way to determine what line or model best fits a curve? Are some equations more complex than others? Does making more assumptions make a theory less likely? Is the principle of proximity that we talked about what you mean when you say Occam's razor? Because it seems to be a common way of referring to Occam's razor, even if it's much weakened in its power, it does seem to be something that many people are talking about when they're talking colloquial about Occam's razor. Is that version of Occam's razor, the principle of proximity, more convincing to you than the kind of more powerful theoretical versions that we should have elegance in our theories, or we should limit the number of metaphysical entities that we're positing? Leave your thoughts in the comments below. Watch this video and more here at Carneades.org, and stay skeptical, everybody.